Thanks everyone. Just saying hi. I'm going to do the intro portion here of this webinar. Just to start, I'm going to play a small video here that showcase, the range and the variety of industry and applications that Rocky is related to. Here it is.
Particles are everywhere. Design and operation of engineered mechanical systems require accounting of particle dynamics. Particle simulation is the key in developing high-quality products while meeting cost, performance, and sustainability concerns. Meet Rocky, the software that is delivering critical process insight for solid handling systems in multiple industries. No matter your industry, use Rocky to accelerate your product development processes.
Yeah, so in a nutshell, the message that we want to convey to you all on this introductory part here of this webinar is that particles are everywhere, and you get impressed by the amount of applications and industries that we are touching today, and helping them to model a lot of different problems which are connected to fluid dynamics, to traditional structural mechanics analysis or electromagnetics, but they do care more details as far as particle representation is concerned. Problems involving different particle shapes, interaction with fluids. For example, here on the top left corner, you can see particles coating, like drugs. Okay, on agriculture side, on healthcare. Okay, on floor care, for example, a vacuum cleaner, right in the middle here, or fluidizations, or bottling or packaging machines, scrubbers for cleaning rough surface, and the list goes on. Okay, so in theory, a lot can be modeled using a discrete tool like Rocky, and a lot can be modeled, through, what we call particles. But I'm gonna get into more details here, okay, in order to explain how we do that, and how we, we consider ourselves, leaders on this segment. So Rocky is a high fidelity simulation software, okay, that captures and accurates the particle flow behavior. So here you can see the boundaries, of this, harvester, but all the grains, okay, that are coming through these feeders, the cutting process, okay, the harvesting process by itself are modeled as discrete elements. Discrete, not solid, but not rigid. They can be flexible. They can be, three-dimensional. Okay. We can handle a lot of them altogether. This is, an example of our, fiber model, which is like a 1D element with, flexibility within, each joint. Okay. And we are touching a lot of sectors. Okay. From consumer products, agriculture, mining, mineral, food and beverage. These were the traditional ones. But more recently, as we're going to, for example, batteries, okay, or additive manufacturing, right? Renewables or green, and all these, environment issues, they all, are related to particle modeling somehow. If you talk about batteries, for example, we discuss a lot about solid state batteries, which is all about handling batteries, handling material, compressing them, compacting them, and the way that you produce, the way that you storage and the energy, it's related to the compaction, to the density of the material. So it's all about handling material, and the way that you produce is actually very related to the way that you're gonna, finish the life of the equipment. How easy it's gonna be to recycle that or not. It's so. If you take a look on the whole this new circular economy that they talk, it's all about managing resources, managing materials, managing particles in a very efficient way, avoiding waste. So this is a big topic nowadays. Okay, and this is just to give you a glance of the sectors that we work with. With Rocky, we can simulate pretty much any type of shape. Okay, from 3D scan, from complex CAD models, 3D, 2D, 1D, as you can see here on this video. Okay, and historically, these were problems that people were doing just with spheres or putting spheres together and taking days or even weeks, doing that in an R&D department in the university. With Rocky and the technology we have, you can actually model this in an engineering time frame, which means couple of hours or a day time frame. Okay, you can set up your complex problem and use your computer or desktop, your graphics card to solve this problem within an engineering time frame. So we're trying to move from the particle modeling just used from academy. We're moving from that perception to actually apply this tool into the engineering day by day. And this is new, okay, and this is our mission within the industry here. And to do that, we actually are solving a pretty basic equation, Newton's second law of motion. We compute particle and each vertex of this particle's contact in a discrete domain. I mean, it doesn't require a mesh. We're not discretizing Navier-Stokes or any other complex equation in a 3D domain. We actually are solving through use of massive computation particle and particle boundary contact, which is written in the Newton's second law of motion. Okay, and you can add physics. You can add a lot of complex physics into that. You can actually compute, particles with adhesion. You can see here on the left, you have, dry particles rolling, and on the right, wet particles. So you can actually consider, forces within particles, moisture, friction, adhesion. You can measure wear, on the particles or on the boundaries that are interacting with the particles. You can put heat and mass transfer, and the list goes on. So it's very complete in terms of physics that you can add, although we're still solving discrete elements, okay? Rocky brings to the table, and the image actually, the videos presented that, complex shapes, okay? We also add, particle modeling, breakage modeling, which means that we can break those particles. We can solve those efficiently using, the GPU cards, okay? We integrate this with the Ansys products for, couples FD analysis and mechanical analysis, electromagnetic analysis. Rocky has some built-in multi-body dynamics capabilities that you can use to, everything that handle, particles, is pretty much moving. So you can model these motions and compute their, displacement as movement as a reaction of the interaction with the particles. We have a super nice API for those that are concerned and working with they want to add their own model, they want to add their own physics. We have Windows and customization framework in Python or in C++ that you can use to add your model, to automate the process and things like that. More recently, we are expanding our discrete models to also comprise not only to solids but also fluid mechanics. So we are launching with this new release smooth particle hydrodynamic solver that is integrated with our solid particle solver, the DM solver. And this brings, a wide variety of industry and applications. So this video just shows, the most important and relevant feature so far from Rocky, which is the ability to handle, for any arbitrary 3D shapes, 2D shapes like, these potato chips here, like we consider them as shells, okay? And the fiber model, which actually I showcased on the other video. And the list of applications, if you just look for particle handling, it's big. It's all about, transporting, conveying, crushing, compacting, milling, lifting, mixing, separating particles, okay? And usually, we came from, traditional fluid mechanics or structural analysis team and groups. We are just discussing and looking at applications on product design. But Rocky also brings you to look at, the production side, because, pretty much close to 90% of everything that is around you today, you are touching or looking, on the production side, they were in particulate form, okay, during a certain stage of their, their life, their production life, okay? So this is a very important topic, but just now we have tools and software that can enable us to model those phenomena. Introductory portion, and I move this to my colleague Alex to continue.
Thank you so much, Marcus. It's always awesome to see, the variety of particles that Rocky is able to handle. Really, a particle is one word, but the reality of it is a particle is anything to Rocky, as you can see, 2D, 3D, 1D, it can be a gummy bear or it can be a screw. It can be really whatever you want, and so many different physics. I think Marcus just showed you, SPH, which is essentially water model as particles. He showed you drying models. He showed you motion and breakage of particles. I mean, it's really wide. It's really awesome to see. My part is going to be much more software application. I'm going to actually run the software in front of you guys and try to demonstrate how that works in 3 different applications. So bear with me as I go through that exercise. All right, fantastic. So the first application I'm going to show you is a transfer chute. Here, the material is represented as spheres for simplification, but really you can go with real shapes if you elect to, which is going to increase computational costs, but also accuracy. And here at the bottom, right, I'm showing you essentially a couple of post-processing we're going to be doing at the end, which is essentially there is an imbalance of particle left, right on that conveyor, and just showing you, the kind of post-processing you can do in Rocky. So this is, the Rocky interface. Let me color the particle by residence time. It's going to make for a much better video. And here you can see the simulation results in the center. So the particles are essentially just right now going down the conveyor chute. There is a little shelf here that allows the particle to stay here. This is actually because they probably realized in their initial designs that those particles were hitting the walls here consistently, leading to wear and tear. Wear and tear, by the way, is something that Rocky can actually give you. If you're worried that this metal piece would become, worn out over time, Rocky can tell you that. And that's actually how they decided to put, those little shelves a little bit everywhere. So you can cover, those particles by really so many different things. I'm gonna go through the list really fast here. And but in this case, residence time is nice. I also like rotational for data. I think it's nice to see as well. The particles don't all rotate in the same direction, of course, etc. Things like that. But you have a lot of different force analysis and things like that that you can display as well. So for instance, I'm going to go ahead and start displaying, the frequency of impact. And here you can see, right, this is the highest frequency of impacts of my simulations. I probably have some more here, but I can also display things like the normal stress. And I can hide the particles to make that a little bit simpler. And here you can see it. You have your high stress areas here, and every time you have a shelf. However, that's a controlled high stress area, as the particle here that I can show again, they act as a cushion to that metal barrier. And all of that is data you can extract from Rocky. right? So it's really a fantastic design tool, gives you a lot of insight into how it works. Now, if you want to go and do some more deeper analysis, we can go ahead and plot a lot of different graphs. So what I'm plotting here, for instance, is the particle count here. So you can see the particle count increase as we are injecting more and more particle at the start, and then it decreases and reach this equilibrium here. So why does it reach an equilibrium? Well, it's because we have all of those particles trapped right here. So how many are trapped? Well, about 900 are trapped. So then you can do other stuff like residence time of particles, interpreted in different manner. This is the residence time of particles that leave the domain. No particle leave the domain in the first 4.5 seconds. So there's no data there. But the first particle that leave the domain really had a residence time of 9 seconds. I can also plot the average residence time of all particles, not just the one that leave. That's what I'm plotting here, right? So just telling you essentially, you have access to an incredible amount of data that I can go here, all of this data, and you can do statistical analysis on any of those data. So that's how you can create things like this now. So here, this is the mass imbalance left-right. How did I plot that? So what I did first is I created this cube region. This cube region is just a splitter. It will only calculate the particles that are inside of this cube region. Let me go ahead. So that's solid color set here, right? And then I created two planes, one for the left particles and one for the right particles. When I color them differently, that means that I can now interrogate all of the purple particles and all of the green particles independently. And that's how I plotted this mass imbalance. And I can see, right, that in this particular design, there is perhaps not a flaw, but something that a designer needs to be aware of, which is there is a lot more particle mass on the right side compared to the left side. So that means more wear and tear on the right side. And that can also mean perhaps you want to do a redesign, balance that out, wear and tear is more even, you're good to go. All right, I hope all of this makes sense. Let me now show you, so I showed you the software, how to use it, but I haven't really changed anything here, right? I really want to stress this out. Rocky is quite simple to use. Perhaps the first setup, takes a bit of time, but there's no mesh. There's no need for advanced CAD capabilities, nothing like that. And that makes the software quite simple to use. Let me show you, for instance, what the quote unquote mesh is. It's essentially just, it's not essentially, it is just an STL file, meaning you go in your CAD, you don't even clean it up. You output an STL file of the not clean CAD, and that's what you get. And Rocky can use that. There are holes here, like the part missing. There's things that don't match at all. Nothing matches here. It doesn't matter to Rocky. The worst case scenario is one particle leaves the simulation domain through the hole, and it's no big deal. Rocky does not care about it. It just disappears as it exits the simulation domain. And so that means that there's very little CAD cleanup involved, and there's no meshing whatsoever. And that makes Rocky so simple to use when you compare that to things like CFD analysis, which requires absolute perfection in your CAD. If two parts are separated by 2 microns in CFD, you will have trouble. Interfaces in CFD, lots of CAD prep, then you have to mesh, and then you have to simulate. In Rocky, it's pretty much limited CAD prep, STL file, and go to simulation right away. So that's pretty awesome. So, and you have also the ability to change things quite simplistically. So for instance, those particles, right? Right now they're indicated as spherical, but it's so simple for you to go here and just say, no, I don't want a sphere, I want something else. And to just select it and run it. So enough talk, let's actually do it live. So let me go ahead, I'm gonna save this. I'm gonna save it as live, all right? And let's just do a bit of work. I'm gonna pretend I'm a designer. I've learned a lot of things. And what I've learned is I don't like this shelf. I just don't like it. I wanna remove it. And then I don't like those spherical particles. I really would like to have more realistic particles to my application. And I'm gonna show you how much time it takes you to do that live and then to simulate it. All right, fantastic. So the first thing you wanna do is you go in CAD and Don't clean it up. Don't lose your time. There's no need for it. And what we're going to do is we're going to do some modification. Here, I just want to remove that shelf. So I'm going to go here. I'm in the CAD. Okay, that's a nice angle. Go in here, select the shelf, delete it, and then File, Save As, and STL file, and Shoot V2. All right, by the way, I've done that in SpaceClaim, which is Ansys CAD tools. You're very welcome to that in SolidWorks or CATIA or whatever your CAD tool is. There's no need to go to SpaceClaim here. Any CAD software that cannot put an STL is fine. So now I have this new STL file. I'm gonna go here, see that's my geometry input. Those are the CADs that I gave to the software. So I'm gonna go here, take my geometry and just say, all right, where is my geometry? I'm gonna load a new file. My new shoot. Yeah, I think it was created in meters. Oh, and now let me rotate around and you see that shelf that we had before, it is gone. So that's the new CAD part. Do I have anything else to do? No, I do not. This is it. The geometry has been changed. I'm ready to run. But I told you I wanted to change a little bit more stuff. So let's go into particles, you know, those spherical particles, great approximation. Everything runs very fast. But let me change things a bit. All right, so I'm gonna do some polyhedrons here. Do I have something else that's funny? Yeah, polyhedron is fine. And what I'm gonna do is I'm gonna do large polyhedrons at the start, and then smaller polyhedron here. All right, and let's see, I think that should run. Let me go ahead and try this out. I also don't want the shoots to see the STL file, so let me remove the edges. There we go. And let me rerun this. All right, I'm saving the file. I'm running the file. Yeah, that went through. And now another, this really blew my mind. You do not have, you can look at the results live. This is what we're doing right now. This is, by the way, computing on a laptop that's about 3 years old. I have a 4th generation, actually it's 8th generation, well, generation 13 of Intel right now. So I'm 5 generation behind of Intel, solving down on 5 cores. So this, I'm not using state-of-the-art machinery here. I'm reusing a standard piece of equipment, the relatively old laptop that everybody can use, and I'm running this live in front of you, and I can interrogate the results as this runs. Something I like to do here when I show particle mass, this really highlights, you know, the fact that I have large particles and small particles in this simulation. And again, all I have to do is go here, you know, fill out that table, change the shape of the particles. You can import custom particles too, right? So if you want to create your specific shape in CAD and then import that, you can too. So you don't have to use pre-existing particle shapes or anything like that. And again, I changed the shape here of the shoot itself, and I'm ready to run, right? So it took what, 3 minutes, 4 minutes, and the simulation time for this is shown here on my really old laptop. It's expected to be about 18 minutes of time, right? So that gives you an idea. This is a pretty simple case, but that gives you an idea, right, of, hey, I have a design. I'm able to understand it much better thanks to Rocky. I'm able to change it in minutes. I'm able to change the particles, and I can get advanced post-processing respect to imbalance, you know, wear and tear, stresses, etc. All right, so I hope this was super helpful for everybody. I'm gonna go ahead and open my second example for today, okay? So I go here, open a new project, and my second example, it's gonna be the tablet coder. So I'm opening that. The tablet coder is really interesting to me because I had no clue why Rocky was able to give the coding, because in my mind I was thinking it doesn't simulate the coding particles themselves. So how does that work, right? So I did this. By the way, all of what I'm showing today is workshops. All of those workshops are very well guided, and I use those guided workshops to achieve what I'm showing you guys today. So it's really not simple is not the word, but if you compare that to FEA and CFD, those are not the same software in terms of learning curve necessary to know them. I'm a CFD engineer. I picked this up 3 months ago, and I've used it every so often, and I'm able to go in Rocky's website, find workshops. They have 25 different workshops, something like that. It's incredibly diverse, and create those cases. So here, what I'm showing today, it's a coding machine. So it's a drum. Very funny enough, right? You recognize this shape. Marcus showed it in a drying application. Drying and coding are very similar application. For drying, often you want to couple that with CFD because you need the moisture content of the air. For coding, you don't have to. I'm going to show you a little bit better how you can simulate coding today. So the first thing you have to do is the rotation motion. So what you do here is you import your geometry. That's the drum. You give that geometry a motion. Let me click on it. It's a rotation at this speed around the, I don't see the axis, but it should be written somewhere. But anyway, it's around the Z axis. Oh, sorry, that's because that's in the Z. So it's a rotation around the Z axis here. By the way, look at this. Those are all the predefined motions if you don't want to enter your custom motions. So you can do translation, rotation, periodic vibration, free body, spring. And you can nest them within each other. So you can have a spring that's rotating. So lots of different motions. So here you imported just a geometry. You specify the motion, specify obviously the materials, bring in the particles. So that's really interesting, right? This one is a custom particle, meaning that particle is not default. It doesn't exist in Rocky. We created it in CAD and we imported that particle inside the software. And then you can also see, right, that we did a volume fill. The last time around for the transfer shoot, the particles were coming through a plane at a predefined rate. So that was what we call a constant fill. But this is a volume fill. So it's just a bunch of particles at the start. You indicate the mass of particle in their location, just a bunch, and you let the simulation go. So it's very simple to indicate to the software. And then you can also do another type of particle, which is custom fill, which is you indicate specifically where each particle goes, at what time do they appear, etc. So lots of different ways to bring the particles inside your simulation. But by and large, why I go through that is just because that's all you have to do. Import your geometry, define your motions, define your material, define your particle. Where are your particles coming from? This is it, guys. There's nothing hidden here. That's it. It's again, simple is not the word. Simulation can always be as complex as you want to make it. But what I'm saying is, it's not going to take you months to have your first simulation results. It's going to take you days, no more than that. And from there, you get smarter, you get better, you make more advanced post-processing, and you get more useful data. But unlike CFD, it's not going to take you months. It's also not going to take a giant, enormous machine because I'm running this on my laptop. I'll bet this one on my laptop was time-consuming. I run that on my cluster instead, 30 cores, about 1 hour on 30 cores. So that's the kind of simulation time for this one, which was quite complex. Now, let me tell you why this is actually a coding application. So here what I'm showing the color, the blue color means that those are particles that are not well coded. The yellow colors are particles that are coded well or more. And essentially what we did as engineers is we brought in those polyhedron, again, not just cat shapes, right? And it's a volume of space where we expect the particles for coding to be, right? So it's just a volume of space. We're not doing any simulation here. It's just post-processing. But we establish a volume of space where we say, we expect that a particle in that space is being coded, okay? And what we say then is we can compute, the residence time of the particle in that space. So that's what I have been doing here. It's the residence time, not of the particle in the drum. It's how much time have a specific particle spent in any of those cones. And that is how I can color that. So obviously you can see, right, At this here is about 15 seconds, and you can see I have tremendous disparity in the coding of my particles. So obviously I need a couple of things. I need to run a lot longer, or I can run maybe at a different speed. How would that be? Running at a different speed, I would go here, motion, change the speed, and relaunch. So 5 seconds of engineering, 1 hour of running on 30 core, and you have your answer. Does it work better at faster speed? Maybe you can run for longer, meaning instead of 15 seconds of physical time, maybe 5 minutes is better. Run that 5 minutes if you elect to. Any way you want. You can maybe change the drum shape, etc., etc. All of this can be done relatively simply, right? And it can indicate to you, yeah, am I getting better or am I getting worse? Like, what do I need to do to better code? I like this histogram, which is a new post-processing I haven't showed you before. This histogram is showing you essentially the residence time in the spray. So that means that if you're on the left, you don't have a lot of coding. So at the start of the simulation, you know, the particles, they don't have any coding at all. Almost all of them are here. In the middle of the simulation, we can see, right, that a lot of the particles have moved toward the right. I still have those two bars, right, with 600 and 700 particles here that don't have a lot of coding. By the time I'm at 15 seconds, I'm sorry about that. By the time I'm at 15 seconds, we can see, right, that particles are almost no coding whatsoever. There starts to be very few, maybe only 100. Right, and then particle with medium amount of coding, 500, and then the particle with decent amount of coding are all the other ones. So at any rate, what I'm trying to show here again was the ability to do awesome post-processing in Rocky, really understand the data, really understand what matters, what does not matter. By the way, another type of thing, you know, you can do very, very simply. I mentioned changing the drum, changing the rotational speed, changing the time the drum is rotating. Check this out. Those spray geometry can be changed here. Super simple, meaning you can scale them up, down, you can make them longer, larger, different angles, whatever has your fancy, just by changing the numbers here. So it's one geometric shape that's deformed. That means, and that's all post-processing again, right? So you can change your sprays and try to find a spray that maybe works better for you. And this one actually will not require a rerun. So really just a lot of awesome stuff you can do just here for that particular simulation. The last thing here, and that's pretty cool because that's yet another type of post-processing I haven't shown you before. This is the frequency of impact on a particle. And what that tells me is that all of the angles, all of the cones, right, they are the one that gets all of the impact. And so that tells me on this particular particle that most likely these things are going to get rounded big time. Like if I'm getting impact at a frequency of 15 hertz, that's going to be thousands of impact by the time I'm done rotating this. That means all of this is going to be rounded. Maybe that doesn't matter for that particular application, but maybe your particle needs to stay sharp. How do you do that if you don't have a good idea of how many times it's going to impact, of the stresses of those impacts, the velocities of this impact? All of that is data you need if your particle should not be rounded, right? So at any rate, Rocky can give you all of this data, visualize it very simply, and you know, allow you to do some modification and rerun quickly. Let me go to my third and last application example here. All right, and this one I like so much because as an engineer, I am almost entirely convinced that you cannot do that experimentally. I am sure we have experimental people in here in this audience, maybe some have even tried, but I don't see a way to be successful experimentally here. This is a bottling application. Again, I'm showing you guys the variety of particles that can be modeled with Rocky. So we created those bottles in CAD, right? They're not part of Rocky. We created them in CAD and imported them. And the goal here is to make those particles single line. So I'm gonna go ahead and play. I think I have a video that I created. Yeah, let me play that video. Is it computing? Okay, let's give that a second. Yeah, I think it's computing the data. So let's just go. So you can see here the bottles are moving and becoming single filed as they move through this, right? And essentially, as a designer, what you want to make sure is that no bottle can fall. That's the most important. If a bottle falls, you're in such trouble. The shocks are not too hard because you don't want to damage the bottles, and then they are becoming single line, you know, and that is fast enough. So that's a lot of things you're trying to work with, right? And you have, I kid you not, you have 13 different belts, all of which can be at different speed. So I'm taking just a second here. How are you going to optimize that system with experiment? Are you going to test 15 different bottles, hundreds of different speeds for the belts, for the 13 belts, and a different cat shape for this S shape? It's impossible. It's way too long. And the big problem here is if you're wrong and you put that in an assembly line and a bottle falls every so often, what do? You have to stop the assembly line. You have to stop the entirety of the production. And now you have to find on the spot the problem. This is not a good place to be, guys. Don't do that. This is a 15-minute simulation, 20 minutes on a laptop with Rocky. And here is how you set it up. Again, your physics, which is essentially what's the direction for my gravity. The rest of the physics is default. Modules, just a way to record more data. You import your geometries. You give your motions. Here, all of the motions are simple translations. You define your materials, you import your particle, and that's it. You are ready to solve. So I hit a little bit of difficulty here, but in the big lines, this is what it is. There is not more than this to it. So don't try to do that, you know, on the field with stopping an assembly line as a possibility. Just use simulation softwares. These are not in a simulation realm. Now let me show you a bit more of what can be done with Rocky in terms of advanced post-processing here. That's going to help you understand if your design is, you know, going to work or not. So obviously the first thing here is we can verify that we're not expecting to have any bottle that falls, right? This was very graphical. There's no problem there, but we can do more advanced stuff. So for instance here, you know, I'm showing two drawings. One is the residence time. Okay, that's pretty simple. We can see, sorry, the particle count, my apologies. So we can see at the start there's no particles. Then there's more and more particles as they come in from the left. Then the number of particles is stable, and then it goes down as they leave from the right? And at the end, I have 0 particle. Great, all of my particle left. Good, doesn't really have a lot of added value here. The next graph I'm showing you is the residence time in blue. As the particle enter, they obviously have a residence time of 0, and then it takes them about 13.5 seconds to go through my system. So that's good information, right? Because now if I want things to go faster, well, my target is to beat the 13.5 seconds, right? So is to beat this 13.5 seconds. But in this particular case, you know, 13.5 seconds is what I achieved with my design. But look here at the end, I can see there's a couple of particles that took more time to exit, and maybe that's of interest to me. So I'm gonna go back and I'm gonna check, why do I have particles at the end that seem to be taking more time? So I go, check. Okay, interesting, and now there you go. Do you see those particles, how far apart they are? Right, and that's why those are the particles that took the most time to exit. And why? Well, that's because when the particles are stacked like this, they enter those left belts that are much faster, and so that's going to make them move faster toward the right. But those last few particles, they remain on this S curve, so they are always on the slowest belt that they can have, and that's why they essentially lag a bit behind. So maybe that doesn't matter. maybe that matters to you a lot, because behind this, most likely you have a wheel that grabs all of those bottles or something like that. And if that wheel is not expecting to have bottles coming far apart, then what do you do? So you have to be aware that this is how your system works, that when you feed that system constantly, you have consistent bottle alignment. When you do not feed that system constantly, you do not have consistent bottle alignment with tremendous spacing change. That's not something that is easy to see, you know, on the line or understand. But in simulation, piece of cake, right? All right, so now let me go to the next step, next level of data analysis. Here, I am showing you guys the maximum impact velocity. That's super important. This is glass material we have here, right? We want to know, is it going to be damaged or not? And so I can see here, all right, I click on Shift on my keyboard so I can see, and at 15, you know, something like 15 and a half, yeah, 15 and a half around. I have a pretty large impact here. I can actually go ahead and check that table here, which is the data. So 15 and a half seconds, bear with me. I'm terrible at this. I think this impact was about 0.6. So let's go and find it. I have a big impact at 0.2 here. Maybe I can go and check it out. So I have a big impact at 0.2 at 15.54. So let me go to 15.54. All right, bear with me, guys. Fantastic. I show this. And now I'm going to color this by impact. And there we go. So I had an impact here. I had an impact here. Now, if I go a bit further, oh, did you see that? I had a large impact here on the S. Let me just go ahead. More impact on the S. I'm seeing a lot of impacts in this area. And that's normal, right? This is the fastest velocity that the bottle achieves with the fastest belt, and they have this S curve. And so that means this is where the most impact occurs. And Rocky is essentially able to tell you, yep, those are the impacts, those are the impact loads, forces. And so from there, you can know if your system is gonna, how your system is gonna react. Is your bottle gonna be okay? Is it not? Now, imagine you have 5, 6 different bottle shapes that may go here. If you are in the experimental realm, you have to test them all. Maybe they have different fill rate. Well, you have to test that too. If you're in Rocky, testing a different bottle is as simple as going here and again, just import a new particle. That's it. You import one file and you have a new particle. If you have different fill content, that's here. You see here, I have a center of mass that I can adjust. Let me actually go ahead and show that particle. That's the particle right here. In this case, the orange point is the center of gravity. Sorry, it's the geometrical center of mass. But the blue dot below is the adjusted center of mass. So essentially, you as an engineer have control over the fill rate of that bottle. You can move that up and down. So not only can you test different bottle shape, you can also test different fill rate. Maybe they have more glass at the bottom, so the geometric, so the center of mass is lower, right? And that's just a small change. Relaunch your simulation, wait about an hour, actually 20 minutes, I think, on my laptop, and you would have the answer as to how does that system performs. All right, so that concludes the demonstration. I'm just gonna take 1 minute, no more, to point out to the fact that I have shown you guys 3 simulations that just live inside of Rocky, but there's more you can do, right? So here you can see there's a CFD coupling that they have brought here. They also have a FEA coupling, but I think it needs you to load a module. But essentially for the CFD coupling, let's say, let me open actually this one. Perfect, the tablet coder. Let's say that you have the tablet coder like before, but now instead of the coding, you're interested in how are they drying, right? So you have dry air coming in, humid air leaving. Well, how is that air gonna absorb the humidity and how is it gonna move inside the drum? That's Fluent. So you would simulate that in Fluent. You don't simulate the particle, you simulate the drum in Fluent with dry air coming in. That's it. Once this is set up, so it's a pretty simple setup, right? Just one drum, no particles, dry air coming in. Once you have this simulation file, you set it up in Rocky, exactly like this. You go here and you say two-way coupling with Fluent. And what this is going to do now is that the flow field information is going to come from Fluent. The particle information is going to come from Rocky. And then we talk to each other. That means that the flow field is going to know where the particles are. Rocky is going to tell Fluent, this is where I have particles. Please create obstructions and pressure drops. And Fluent is going to say, okay, I created those pressure drops. Here is my flow field, flow velocity. Here is my flow temperatures. Here is my relative humidity. And then Rocky is going to say, oh, this is the kind of velocity, temperature, and relative humidity I have around these particles here. Then this is my drying rate, etc., etc. And those two softwares are going to communicate until you have, a nice drying curve for your particles. Or it can be forces that you're interested in. So for instance, here, obviously the motion of the particles is due to aerodynamic forces. So you need Fluent to calculate where the flow is going, and Rocky to calculate where the particles are going. And when they talk to each other, you can do fluidized bed, you can do lots of things. Here, it's a coupling with FEA. That means that Rocky can calculate the force on the structure, and it can do limited FEA analysis. But you can send all of those forces to mechanical, Ansys mechanical, and then you can have the full power of a full-fledged flagship FEA software to in detail measure stresses, deformation, whatever you're fancy. And finally, smooth particle hydrodynamics. Marcus talked about this for a second, so you're a little bit aware of it. But essentially, sometimes it's better to have Fluent coupled with Rocky, but it can be computationally costly. And so there are times where you just don't want to go there. You don't want to pay the computational cost to have Fluent running in the background. You're just interested in perhaps a simpler model. And that's when the smooth particle hydrodynamics, SPH, is going to come in. And so that's what's going to allow you to do simulation with both water and particle if you want, for, again, a variety of application. I absolutely love this image because those are like waves that are happening in this room. I just think it's so pretty. And by the way, that would be unsteady and you would be able to watch those video lives and simulate this kind of physics live much faster than you would with a full-fledged CFD software. Perhaps not as accurate, but certainly powerful enough that you can find a lot of engineering applications for it. And that's pretty much it. So a couple of takeaway. I'm gonna take my breath. I've been talking for a while now, but a couple of takeaway. Rocky is versatile. Have you seen the number of applications we've shown you right in an hour? You can do mining, farming, pharmaceutical, heavy equipment, so many designs, so many particles you can do. It's incredible the amount of different physics you can have in there. It is fast, right? On top of my head, it was about 10 minutes on a cheap laptop. Well, on an old expensive laptop for the shoot, 25 minutes maybe for the bottles, and on the mic cluster, 30 cores, 1 hour for the coding application and drum. It is powerful. Rocky can be coupled with CFD or FEA software to tackle enormously difficult simulations, things that honestly were not imaginable 10 years ago, maybe even 5 years ago. But now it's sort of common, or things that are becoming more and more common to do this. Just because your designs need this kind of simulation, the fact that it can happen now, it just opens so much more business for Rocky. And it makes a lot more sense in so many more applications, specifically drying, which I've worked in a couple of times. It's so hard to study drying, it's so hard to experimentally make a dryer. I'm gonna take one example, which, I work with a client and we had a dryer and we're trying to redesign it because it took 4 hours for particles to dry. And we realized in those simulations that no, it doesn't. The particles are dried in an hour, but it's just that where the probes are, at this specific location, it takes 4 hours, but that's just a couple of particles. How do you know? You've been doing the same thing for 10, 15 years, but you don't have simulations. When you bring simulations, a week later, the answer is no, actually your system works 4 times faster than you thought it did. And that's what Rocky can bring to you. It's the insight, the ability to tackle very advanced problems and to see why it works better. It's also intuitive. It's much, much easier to learn than CFD or FEA because we know how rocks move. Like, it's not like we need to generate a sense of how they should move. We know how they should move. What we don't know is the statistical analysis of their motions. That's where Rocky comes in, right? And it's all of this post-processing. That's the value. How the rocks move, we can do it in our minds. That's fine. But how does that motion changes the forces and the wear and tear on that metal piece? That I can't. And that's intuitiveness is what makes the software so easy to learn, so easy to set up. And finally, it's effective. And effective, I'm going to take a minute because there are two meanings that I want to check here. It's effective because it can help you visualize how your system works. It's effective from an engineering perspective for you to make a better machine or to anticipate problems before they ever occur. That's effective. But it's also effective because you can now go to a client and you can show him that. You can show him, hey, this is working. This is why it's working. Look at your potatoes. They are going up. None of them are falling. It's fine. Look at your fertilizer. It's spreading exactly as we expect. Those are the statistical analysis curve of where the particles are going to fall, etc., etc. You can use these marketing images not only to make your system better, but to tell your clients, no, I'm not telling you I am the best. I am showing you that my system is the best. Here is how it looks in action. Here is the improvement we have done since we've used simulation, etc., etc. So you can use Rocky, sure, to make your machine better, but it's very important to also focus on the sales. You can also use Rocky to sell more machine because you now have the ability to tell a bottling assembly line, hey, look, we tested our bottles on 20 different, we tested our single filer on 20 different bottles, 60 different fill rates, 5 different, bottom shapes, and they all worked fine. You can show that to your clients, and before you just couldn't. So that can, separate you from the competition as well. On behalf of Ransim and ESSS team, we'd like to thank everyone for attending. And please feel free to reach us if you guys have additional questions or you just want to continue this conversation. Thank you so much, and you all have a great rest of your days.